We've been discussing parabolic partial differential equations. We've looked at explicit methods, implicit methods, and numerical stability analysis of these time-marching methods. We have two more major issues to look at. One is how to deal with nonlinear terms, such as convective terms that we see in fluid mechanics and heat transfer. And the second issue is multidimensional problems. We've been looking at spatially one-dimensional problems, which of course isn't very exciting. So how do we adapt these methods to multiple dimensions, x and y, or x, y, and z, 2 and 3D scenarios? So in this video and the next video, we're going to look at how we deal with nonlinear convective terms. So let's look at the unsteady 1D Burger's equation. We've looked at the Burger's equation before in the context of methods for elliptic PDEs where we didn't have the time marching. Now we're going to include the time marching aspect. So we have diffusion terms, nu times partial squared u partial x squared. You notice this looks like the diffusion term in our 1D unsteady diffusion equation, except now instead of alpha, we have nu, which is the viscosity. We have a convection term now, u times partial u partial x, which as you can see is nonlinear. So adding convection into the problem introduces nonlinearity into the equation. And then we have our unsteady term, the partial u partial t. So we've been looking essentially at this equation before, just with alpha instead of nu. And now we're going to include this nonlinear convective term and see what the impact is when we apply the first order explicit method and Crank-Nicholson method in this particular video. And then in the next video, we'll look at upward and downward differencing and how that works in this context. So the first order explicit method. So remember the first order explicit method, the x marks the spot is at the previous time level. So all the x derivatives, the spatial derivatives, are at the nth time level. So here's the partial u partial t. That's a forward difference in time. It's only first order accurate. Here's the partial squared u partial x squared using a second order accurate central difference in x, but at the previous time level, so the nth time level. And then here's the same thing, the first derivative applied at the previous time level, so ui plus 1 n minus ui minus 1 n. Then we have the u out front, so ui n out front. Okay, so this is second order accurate in space, but only first order accurate in time, just like before. We just want to see what is the difference now when we include this blue convective term. Well, if we do the same procedure as before, put the unknowns on the left and the knowns on the right, we get this expression here. If you take out these blue terms, you get back exactly the first order explicit method that we had for the 1D unsteady diffusion equation. These terms come in because of the nonlinear convection term. This CIN, this is known as the Courant number, and it's UIN times delta t over delta x. Of course, this is the time step, this is the spatial grid size, and then we have this velocity at UIN. So once again, we have an explicit expression, very easy and natural to evaluate. You just sweep across the grid at each time step as you march forward in time. So this first order explicit method, when we apply it to our 1D unsteady Burger's equation, is no more difficult to implement than in the linear case. So that's nice. However, it turns out that numerical stability actually gets worse. It was bad enough in the linear case, it gets even worse in the nonlinear case. Let me show you why. It turns out that stability requires what's called the mesh Reynolds number, the RE delta x, so that's a Reynolds number, but using as the characteristic length scale, the mesh size, delta x, has to be between 2 and 2 divided by CIN. Remember CIN, that's the Courant number. So one of the issues is, of course, I don't know what CIN is. That involves UIN, which I don't know. That's part of the calculation. So I'm not even sure what the criteria is on delta t in order to remain stable. But I do know that this is extremely restrictive in practice. So those two things. I don't know u ahead of time, and it is very restrictive. Let's take a look at the Crank-Nicholson method. Now remember, we like the Crank-Nicholson method because it's second order accurate in both space and time, so that's good. And we did that by putting our x marks the spot, the location of the approximation to the differential equation, midway between the two time levels. And we did that by averaging between the next and the previous time level. So let's apply that same approach now with the u partial x term that we now have. This is our second order accurate central difference in time. Then we take the average of the second derivatives to give us the value in the middle. We take the average of the first derivatives to give us the value in the middle. So that's why we have this 1/2 out in front to get that average. Then notice this UIN plus 1/2. We also need UI at that intermediate time. We get that by averaging across the time levels, just like we do for the derivatives. So now, this second derivative, we use second order accurate central difference approximation. This second derivative, we use second order accurate central difference approximation. And then this one and this one, we also use second order accurate central difference approximations. And we get this mess. So here gives us this gives us this gives us this, and this gives us this. Second order accurate in both space and time. The price we pay is a much messier looking equation. But now, when I pull the unknowns over to the left, knowns to the right, this is what it looks like. I have a coefficient times UI plus 1, coefficient times UI, coefficient times UI minus 1. So again, this is an implicit tridiagonal finite difference equation. Very similar to what we had before. It's just that now we have these additional terms because of the nonlinear convection term. Anywhere you see these capital C's, the Crank number, those came from those convective terms. And then this is all the stuff on the right-hand side where it's UI plus 1n, UIn, and UI minus 1n. Okay, so again, that seems fine. Looks just like the Crank-Nicholson method that we had before for the linear case. But if you look more closely, and remember that CIN plus 1/2, well, that involves UIN plus 1/2. I don't know UIN plus 1/2. That's part of the calculation. This is the average at the previous time step, which I do know, and the next time step, which I don't know yet. So because of that, this approach requires iteration. So let's walk through that. So we have our time marching just like before, do a calculation to get the current time level, that t plus delta t to get to the next time level, do another calculation. So the time marching is the same. But at each time step, whereas before, for the linear case, we just did one tridiagonal solve for the Crank-Nicholson method, and then we could move on. Now we need to iterate. So let me describe that iteration. We're going to start with the initial condition for the iteration being UIN. That's the solution at the previous time level, the nth time level. The k here will be our iteration number. N is the time step. Then we increment the iteration k. We update the UI n plus 1. It involves solving this tridiagonal system. So every time we do step 2, we're doing a tridiagonal solve. Once we get the new solution for u, we can then average the previous and the new value to give us a new approximation for UIN plus 1/2. That then goes into the Crank number that you see here, 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 and here. And then we go back and repeat that. So we go back to step 2, increment the iteration number, do the calculation again. Again, another tridiagonal solve, get new updated values of u at n plus 1, and then update the UI n plus 1/2. And we keep doing that, iterating until it converges at that time step. Once it converges at that time step, then we can march forward to the next time step and do the iteration again. Now this is just a rule of thumb, but in practice it shouldn't really take more than 10 iterations or so at each time step. Now if it does take more than about 10 iterations, that's usually a signal that your time steps are probably too large and you need to use a smaller time step. Remember, for elliptic problems we use Picard iteration for this case. So we were lagging the u out front of that first derivative that made it nonlinear, and we lagged it from the previous iteration because once we got the converged solution, previous and the current were the same. Here we want an accurate solution for u at every time step. So that requires this iteration in order to get the accurate solution at each time step before we move on. So for unsteady nonlinear convection, explicit methods have very restrictive time steps for numerical stability, whereas implicit methods require iteration at each time step. Nonlinear problems are always going to be harder than linear problems. There's always going to be more computational time and effort required. Now in the next video, we'll look at how we can implement upwind downwind differencing as we did in the elliptic case, now in the parabolic case as well.